Alright, you guys, today we are going to be learning about polynomial functions. This is just going to be an introduction, and then we're also going to be learning about the end behavior of graphs. So for our first thing I want to go over is actually defining the general formula for our polynomial functions. So a polynomial function is a function of the form like this. So we're going to see the f of x, which also represents y, equals a n x to the n plus a n minus 1. So what that means is that it's going from your leading coefficient, which is the a of n. So right here the a of n is called the leading coefficient. And then, so that's just the a of n part that we see here and here. These are all the leading coefficients. And the n minus 1 is just stating that it's for the previous or the next term. So you're one less than the leading coefficient. So remember, with our highest degrees, we're in standard form. Our highest degrees are listed first. So then that means would be n minus 1 would be the next highest degree. So for example, if we had a degree of 3 here, then that means our degree would be 1 less than that, which would be 2, and then it'd be 2 less than our original one, so 3 minus 2 would be 1, and so on. So that's what that actually means, and we're going to start with higher degrees as well. So I'm going to go over a couple different examples here where we did go over classifying our polynomials based on the degrees, and we also want to start giving the leading coefficients. We're going to be working with leading coefficients a ton to figure out the end behavior of these polynomial functions. So for our degree for this general formula, our degree would be n, and then our leading coefficient was the a of n, just to give you a heads up for that general formula. So for our function here, we have just a constant value there. So all constants have a degree of 0, and that leading coefficient is actually just 4, just an actual constant. Then we have our degree of the negative 5x plus 1. Make sure we're in standard form, which we are. Since we have a variable, we do actually have a degree of 1 here, which means that we have a linear polynomial. And then we have our leading coefficient. Since it is in standard form, that negative 5 will be my leading coefficient. Squared here is my degree. We don't have our double variables, so we don't have to worry about adding our degrees here. So we're just kind of going nicely down. That leading coefficient on that squared degree is 12. We have 3. Our leading coefficient, that's like that little invisible number in front of that x, is negative 1. Our degree here is 4. And again, I'm just looking at, these are all written in standard form for us, making sure we have to be in standard form. And then our leading coefficient is a negative 3 there. Then we have our 5, degree of 5. And our leading coefficient is 9. So again, make sure you guys, that's why we had to make sure we were familiar with those terms, because those values are super important to be determining the end behavior of our actual degrees. So now we're going to take a look at our polynomial parent function. So this is graphically what we've been actually working with. So that little chart where we had our constant function where it was a degree of 0. So let me write our degree of 0 here. Let me just write an equal sign. So our degree is 0, which means it is a constant function, and then our function that we would actually look at would be f of x equals our constant. So it's just going to be the actual letter there, or sorry, just a number. It'll just be a number there of our constant value. So this is what our constant is. It's just the straight line that we see on our actual graph. Then we have a degree of 1 here. I'm just going based off of our chart here. So look, if we have a degree of 1, and then we're using the notes from last unit, then that means that we would have a degree of 1 here, and it would be a linear function, which we actually have. And then our linear function, we would have f of x equals x. It has to at least have a variable in it, or it could be x plus 1, x minus 1. We're just in our y equals mx plus b form in order to graph that. Our next one is going to be a quadratic function. Quadratic means that we have a degree of 2 then. That degree will always be a 2. And then our function, so again, these are just parent functions. That means that they have no shifts or anything. They're just going through, like here, this one just went through the origin, so that's why it's just x. This one is just going to be an x squared. That's why it's going through this origin as well. It doesn't have any shifts or anything yet. We will be dealing with shifts later. Then we have our cubic polynomial, our cubic function, which will have a degree of, hopefully you guys can guess it, degree of 3. And then our degree of 3 will just have our f of x to the x equals third, to the third power. Let me scoot that over so you guys can actually see. Hopefully you guys have more room on your guided notes with you. And there, I don't know if that's any better. So x to the third. Okay, so you should always have a to the third power of our degree there. Then for our next one, we have a quartic function, which means that we will be having a degree of 4. And then our degree of 4 will just look like our f of x, x to the fourth power. Then we have our quintic, which will be our degree of 5, and that would be our f of x equal to our x to the fifth power. So again, these are just our parent functions that they just go through these values of the highest degree. So when we actually are looking at these functions here, we can kind of determine the number of degrees that would actually, we would actually see how many times it actually goes through the x-axis. So see how we have a degree of 0, which means it's not going through our x-axis at all, so I don't have any x-intercepts there. Degree of 1, it's going through our x-axis once. Degree of 2, if we actually, so these are just our parent functions. If we were to actually draw a graph like this where it'd have a shift, we could potentially have 2 x-intercepts, degree of 2. Oh, I forgot to write my 3 here. So degree of 3, which means that, so again, this is just the parent function. However, it could turn into a function that would cross the x-axis 3 times, still looking like a cubic. So 1, 2, and 3. The same with our fourth degree, that this could end up looking something like this, crossing our x-axis 4 times. Degree of 4 means we have 4 x-intercepts, or 4 zeros even, those are called zeros, and then 5, we would even have crosses 5 times. Oops, back up real fast. So it can go up and go opposite. So 1, 2, 3, 4, 5 times it crosses with the degree of 5. So with that being said, the maximum number of times the graph of a polynomial function may intersect the x-axis is going to be the same as the degree of our polynomial. And then that's how we can actually determine how many of our crosses the actual x-axis, which would mean our zeros, our intercepts, all those roots, that's all the same words there. So that's the same as the degree of our polynomial. Okay. So then the next part of our notes, you guys, we're actually going to be doing this in class because I want to kind of explore with you on Desmos on this. So when we go on Desmos, we're going to be kind of determining what the general function actually looks like, and we will be taking, this is what our end behavior here will start actually being notated as. So we will go over these 5 examples in class when I see you, as well as this. We'll start talking about positive, negative, even, and odd degrees. So wait to fill out your question comments and something to remember on your little bubble at the very last end of that, because I want to go over the rest of the notes with you while we're in class. So I'll see you then. Thanks.